So in the last screencast, we left off on the fact that the Earth's crust and upper mantle, so the parts that make up the lithosphere, are constantly in motion due to the convection currents within the mantle, and also due to the areas in the crust where some of that magma, that melted rock or semi-molten rock, can come up to the surface and either lead to a spreading zone or perhaps a volcano, and that as this crust was pushed, in this case continental crust pushed against an oceanic crust, there is an interaction. So now we're going to look at the theory of plate tectonics, which is how these plates are moving and interacting. So back in 1912, a man named Wegener, which perhaps you pronounce Wegener in German, who was a meteorologist, came up with a theory of plate tectonics. And the geologist at the time dismissed his idea because he was a meteorologist, not a geologist. But what this man noticed was that the Earth's continents fit together like jigsaw pieces. So if you looked at, say, South America here and slid it closer right over to Africa here, these coastlines would actually kind of line up. If you moved North America over as well, you would see they would line up with Northern Africa and Eurasia. Particularly if you took this piece of continent here, Greenland, and moved it down as well. And it would all fit together like a puzzle piece. So in his theory, the surface of the Earth, the lithosphere specifically, is divided into plates. And these plates are almost always in constant motion. And that motion might bring them farther apart or bring other pieces closer together. Now, over time, many pieces of evidence were discovered that supported his idea. So first, let's look at fossil evidence. In the example from your textbook, fossils of a freshwater reptile were found here in South America and here in Africa. Now, this is a freshwater reptile, and this is a great distance of salt water between them. So it would not make much sense that this freshwater reptile would be able to swim across the ocean and land here. It would make more sense that South America and Africa were once united. And it wasn't just this one particular fossil. At various points throughout, for example, for here and here, there were similar examples of species that could not have migrated great distances across the ocean, but were present in both locations. In addition to fossil records, there are also certain rock types that can be found in a location on one continent, and its similar rock type found on the same coastal location of another continent, and so forth as they go up all the way through North America and moving up through Eurasia. And in addition to that second thing, the rock type, they can now identify the relative age of the rock, and found that the age of the rock here was the same as the age of the rock here. But right down here in the middle of the Atlantic Ocean, the rocks were younger than the rocks here and here. And that was because of what you saw before, where there was a spreading zone in the middle of the ocean, which was pushing the older rock further apart and pushing the continents further apart and bringing up younger rock, new rock from the mantle that then made it through to the crust. Now, I want to point out a few things that are sometimes confusing to students. So here we have a map of the world and some of the different types of plates. All of these things with solid lines are plates. Some of them as you see, let's take the North American plate here. The North American plate constitutes all the way here from California, all the way over, and doesn't end here. The North American plate ends here at the orange line. So all of this is moving. So the Earth lithosphere underneath the ocean is also moving with the North American plate moving westward. Now, this map is color-coded. The orange is a spreading zone, so you can see that it's pushing the rock in this direction and in this direction. The blue represents a subduction zone, which is where one plate is being forced beneath or subducting beneath another plate. And so that's occurring, for example, here. Okay, so the plate does not have to follow the continental border. It can include ocean plates. And here, for example, is one very large Pacific Ocean plate. Now let's look at the different types of boundaries and what's going on. Picture A on the right shows a divergent plate boundary, such as the one found in the middle of the Atlantic Ocean. So in a divergent plate boundary, the molten rock is coming up close to the surface here, depositing fresh rock that will solidify as it cools, and it's pushing the rock on the one side in one direction and on the other side in the other direction. So again, that's what we're seeing here. This is a divergent plate boundary. Some plates, though, when they meet, one is forced to go under another. That's the area we're calling a subduction zone, shown in blue. So when two plates meet, one is forced to go beneath the other. And then as it does, this rock is pushed into the mantle and melts, and this rock continues to move in this direction. So that's a convergent plate boundary. And last is the type of boundary that we find in California. That's a transform fault boundary, where some of the one plate is moving in this direction and the other plate is moving in this direction. And it could be the reverse. This plate could be moving in that direction while this plate moves in that direction. So either way, it's a transform fault boundary. And that's what's taking place here along the coast of California and Washington State, etc., all the way up here to Alaska. So there is a movement of the Pacific plate that is moving it basically northwest. And the North American plate is moving southeast. And as they do, they're pushing against one another very tightly. And pressure builds up, and eventually there's so much pressure built up that the two plates, basically, the pressure makes them slide past one another a little bit further each time. Now, the last piece of evidence that is now going on is that we can actually measure the movements of these tectonic plates. And in some places, like in North America, we are moving about 2 inches per year. And that's an amount that is measurable in short periods of time. Okay, so next we are going to look at what happens when the plates come into contact with one another. So first, some definitions: faults and earthquakes. A fault is a fracture or break in rock across which there is movement. So it could be movement in any direction, but it's movement. Second definition, earthquakes. Earthquakes occur when the rocks of the lithosphere rupture unexpectedly along a fault. So at this point in time, we can't predict when an earthquake is going to happen. They take place typically very deep below ground, where we don't have the ability to measure the pressure that's between these two rocks, and therefore when the pressure will be so great that there will be some movement. Next definition is epicenter. An epicenter is the exact point on the surface of the earth directly above the location where the rock ruptures. So, the textbook gives the very dramatic example of a part of the San Andreas Fault. The San Andreas Fault is a large fault that runs all along California coast here. Here's this part of California is part of the Pacific Plate, so it's moving basically northwest. And this part of California is part of the North American Plate, and it's generally moving southeast. So usually these faults, the vast majority of time, these faults are deep within the ground. You don't see a big opening like that a person could trip and fall into, or when there's an earthquake, the ground is not going to open in front of you and swallow you up. So I don't particularly care for this photograph as an example, but hey, we'll have to deal with it. So here they're showing you that an earthquake can take place deeper in the ground, but directly above on the surface of the earth, which will feel that movement, that is called the epicenter. So the epicenter isn't down here where the earthquake happens. The epicenter is up here on the surface where the movement is felt. Okay, so next I want to tell you about the Richter scale. The Richter scale is the measurement of the largest ground movement that occurs during an earthquake. So it's much like the pH scale. It's a logarithmic scale. So for example, if you have an earthquake of 2 points, that's measured on the Richter scale of 2.0, that amount of ground movement is not very much and probably won't even be noticed by most people. If you move to an earthquake that's a 3.0 on the Richter scale, that 3.0 earthquake is actually 10 times greater than the 2.0. And then if you move even further to say and that's where you start to have people notice an earthquake. If you move up to an earthquake on the Richter scale that's about a 4, then most people would notice that earthquake, would have felt that earthquake, because it's 100 times greater than the amount of movement that took place at the 2.0, 10 times greater than the movement that took place at the 3.0. So each time you go up the Richter scale, the severity increases quite a bit. So let's take a look at a few earthquakes. Let's see, we have here the earthquake in Haiti that led to those mudslides and all that disaster not that long ago. That earthquake was a 7.0, which is a very significant earthquake. The earthquake in Northridge in California, it's basically a suburb of Los Angeles, that caused a lot of damage as well, including some deaths. That earthquake was a 7.8, again, a serious earthquake. The one in Japan that caused a tsunami, so the earthquake took place in rock that was under the ocean, not on the continent of, not on the country of Japan or its surface. And that caused a tsunami, and that earthquake measured a 9.0, extremely significant earthquake. And then the earthquake that was the highest on record was in Chile in 1960, and that was an earthquake of 9.5. So those are all very, very serious earthquakes. This recording is being made November 2020, and we just had a 3.4 earthquake centered in Buzzards Bay, and some people in our class observed the earthquake, or their family members did, and others of us did not even notice it. So that's a 3.4. We are at some distance from Buzzards Bay, but not that far. Okay, so 3 things I want to tell you about safety during an earthquake. So yes, first of all, we in Massachusetts are subject to earthquakes, though they have not happened frequently or been on a very large scale. But there is a major fault line that runs